Okay, good morning, everybody. My name is Fergus Dolan. I work for NALA, the National Adult Literacy Agency. We're delighted to welcome you here to our webinar this morning on strategies for teaching fractions for understanding. We're delighted to have Dr. Niamh O'Meara from the EpiSTEM Centre in the University of Limerick to present. And Niamh has, just for anyone who's joined in the last minute or two, Niamh has urged you to respond to her questions. She's going to throw out questions to you and she wants you to respond. She called me back in then to call out your responses, your thoughts, your opinions. So if you could get typing in the questions box when Niamh throws out the questions to you, that'd be great to make it a little bit interactive because it's quite difficult with a webinar. So over to you, Niamh, and all the best.
Thanks very much, Fergus. And I just want to say thanks to Fergus and to NALA for giving me this opportunity again this year. It's one part of my job that I really love every year when Fergus gets in touch to say, would you be interested in delivering one of our workshops during Maths Week? I find engaging with the tutors that are involved with NALA so worthwhile, and it's always a really positive experience, and hopefully, although it's different this year, that it'll still be that positive experience. So as Fergus said, I will throw out questions in the hope that we can get some interaction going, because that's the key to a successful workshop and in this case a successful webinar. So I'm just going to start by throwing up 4 questions. I'll give you a second to read through them. I'll then talk to you just for a minute or two about kind of what is understanding, but while I'm talking, if you can be considering maybe your answers to those questions, and as Fergus said, I really would love to get your insights into this. So the questions that I'd like you to consider: why do we need to learn about fractions? So again, it's such a common student question from primary school right the way up. Why do we need to do this? When will I ever use this again? So that's what I'm trying to elicit here from you. So why do we need to learn about fractions? What purpose do fractions serve? And when and where do we encounter them? And what might we not be able to do without a solid understanding of fractions? So they're the kind of questions. I'm going to give you a couple of seconds now just to digest those questions. I'll then chat to you for a couple of minutes and I'll come back and we might be able to have a conversation around those questions before kicking off and getting into the real nitty-gritty stuff. So again, it's why, what, when, and what might we not be able to do without a good understanding. So if you can just type away, again, I just think the workshop will work a lot better, run a lot better if we get some feedback from you. So what, why, when, and what might we not be able to do? So just then what I want to talk about just for a second, while you're kind of digesting those questions and composing your answers, what does it mean to understand? So you can see from this workshop that there's such a strong focus on understanding. And what you might often hear, and we've done a lot of work in EpiSTEM in relation to this, is teachers saying, I'm under such pressure to get the course covered. Okay, and that again from every walk of life, whether that be the primary school curriculum, the secondary school curriculum, or I know from talking to tutors like yourselves before that there's a lot of content to get covered, whether it be level 3, level 4, and time does become an issue. So people are looking at covering material. But really when we're talking about teaching for understanding, we're not talking about just covering it, we're talking about unpacking it. So what does understanding mathematics actually mean? Well, it means being able to do it. So in terms of fractions, it means being able to add a third plus a quarter. So today I will look at how we actually do some of those operations or perform some of those operations. Understanding mathematics means to be able to solve problems. So again, I'm going to put a strong emphasis in one section of the workshop on how do we actually solve real life problems that involve fractions. Again, applying or applications, that's very similar to what I've just discussed. Making connections. So again, when we look at the idea of division of fractions, we're going to go back and try and connect it to, well, what does division of whole numbers mean? Because oftentimes, when students do not understand the division of fractions, it actually is that they don't understand the concept of division in the first place. So we need to make those connections. And we need to make meaning. Okay, so it's really important that they understand the meaning behind the procedures. So again, we're never just going to look and say to students, oh, just take it and learn it off. Okay, we're going to try and move beyond that today. And we're going to be able to try, or we're going to try, to transfer knowledge. So in order to understand mathematics, you should be in a position to transfer your knowledge. And that's always a good check of understanding too. So teaching for understanding then, what does it mean? We develop deep conceptual and procedural knowledge. So what's the difference there? Well, procedural, let's just take an example of a half plus a quarter. Procedural means knowing how to actually add them. Conceptual means knowing why we undertake those steps. So that's the slight difference, but a really important difference. And what's important to recognize or to remember is we don't want one without the other. So it's not that we want to put all the emphasis on conceptual, because procedural is still important. We need to find a balance. Posing problem-based instructional tasks. So again, we look at that a bit today. Engaging students and providing guidance and support as they develop their own representations. And representations is a really important word and will be a strong focus of a lot of what we do today. Then highlighting where students will encounter concepts in their everyday life. So again, we will look at that. Promoting discourse. That's going to be a bit trickier today. Okay, just because of the virtual world we find ourselves in nowadays. But again, please God, we'll only be teaching in a COVID environment for another couple of months. So we do still need to be aware when we get back to whatever our new normal is going to be, we do still need to be aware that discourse is really, really important. And even in our virtual world, finding ways to encourage discourse, as we've just done at the start of this workshop. So summarizing the mathematics and highlighting effective representations and strategies, again, that's summarizing or the consolidation. We look at how we can do that, but it's another critical part of teaching for understanding. Challenging them to apply their knowledge and listening to students. So that's what teaching for understanding entails, and that's what I will kind of be hoping to show today. So now, back to those warm-up questions. So why, what, when, and what might we not be able to do? So Fergus, I might just call you back in there just to see, is there anything in that chat that I can't see at the moment?
Yep, we've got a few responses, Niamh. So Itziar Lassa says fractions are present in everyday life.
Super. And that's true. Like, very few things that we can look around at and not see fractions. And we'll talk about that in a second.
Catherine Dillon said the why question, saying fractions are used in everyday life. Actually, same thing, yeah. Catherine Hurley saying not always dealing with whole numbers. Catherine Hurley then said important for working out percentages. Catherine Dillon saying when using currency, discounts, etc. Adrienne is saying to understand what portion of a whole number you have. Fractions enables you to break things down into portions. And finally, Adrienne is also saying help with telling the time.
Excellent. Okay, we've got a really, really good start point, and thank you very much everyone for engaging with that. So a thing that came across a couple of times was it's in everyday life. So if we look around us, can we see some object, some item that actually would involve fractions? So I'm just sitting here in my kitchen and straight away I'm thinking anything to do with baking. Any kind of measurement, whether it be a jug or so on, half a cup, quarter of a cup, half a teaspoon, we see fractions straight away. And again, hopefully you can all look around the setting you're currently in and say, yeah, I can imagine where fractions might be used then. So that was the first thing, everyday life. Let's talk about, people gave some great examples. So currency, discounts, time, and we'll talk through those more in a second. So really excellent examples. People also said, they mentioned percentages and the link between fractions and percentages. And this is what we spoke about in terms of the need to develop connections. And that's really, really important going forward. And then I was really happy to see someone talk about proportions, what proportion of a whole number, and allows us to, and that word, nearly sure Fergus used the exact word, break it down. So there was that word break was used, and we'll come back to that in a second. So thank you again for that. So just an introduction then. And one nice way to introduce a new concept, and we could be talking about any concept here. We could be talking about number systems, we could be talking about geometry, we could be talking about trigonometry, is to actually break down what the word means. So the word fraction was derived from a French word, and again, pardon my pronunciation, fraction, I'm going to give a guess at, and that was in the 12th century. And also it links with the Latin term fractional, again, pardon the pronunciation. And both of these terms can literally be translated to mean a breaking. Now we can start to see, well, what we mean by a fraction. It's the breaking of a unit. And again, just that literal translation can be so, so helpful for students to say, do you know what, this is just it's something straightforward. It's not overly complicated. And that's what a fraction is, the breaking of a unit. Likewise, and I was saying we could do this for so many other topics. Trigonometry, if we break it down to trig, that means triangle, again, linking back to Latin terminology, and metry, measure. So trigonometry is simply triangle measure. So again, the literal translation of these terms can be really important just to ease students into a topic and to show them that it's not as daunting as they feel. So it's part of a unit or part of a whole. And I think what Adrian said exactly that, the proportion of a whole. So again, just the fact that it's breaking a unit up, or it's breaking a whole object up, and that's what's giving us the fraction. And again, it shares its origins with other words that students would have seen before: fragile, fragment. So again, what does fragment actually mean? It means a part. Fragile, easily broken. So it's all linking back to this idea of a breaking. And again, where do we see them? So as I said, you mentioned some excellent examples already. I just want to look at one or two more. Some have been said. Shopping is an example. You might go into a shop, see a half price sale. What does that actually mean? Likewise, someone said the link between percentages and fractions. So what does it mean if there's 20% off a pair of shoes you've been looking for? How do we relate that to fractions? Sports. There's very few sports we can turn on now without seeing some reference to fractions. So some of you might be familiar with American football and you've heard of a quarterback. Okay, you might hear in Gaelic football the half-back line. Half-time occurs in most sports. And then you have ice hockey, where they name them quarters, but really there's 3 of them in a match. Doesn't really make sense. But is it just that it's better than we call them thirds? So you can't get away from fractions when looking at sport. Measurement. So again, if, as I said to you, when you looked around the house, hopefully you might have seen, or wherever it is that you are, you might have seen that not everything is measured in whole units. Okay, so there might be a table that's 1.5 meters in length. Okay, and again, it's really, really important that we then have a deep understanding. If we want to tile a floor, if we want to paint a wall, we need to understand measurements. And they're not always, particularly in the real world, you know yourself, things just don't always end up being whole numbers. This was mentioned already, the time. Now, this is a real Irish thing, I think, as well. If you go to America and you say, someone asks you the time and you say 4:45, they look at you completely blankly. But for us in Ireland, that's second nature to us. Yes, it's 4:45, meaning it's a quarter of an hour to go till 5 o'clock, or 5:15, it's a quarter of an hour past 5 o'clock. So again, telling the time, and students are able to tell the time from a very young age. So we just need to build on that when we're teaching fractions. And you can see recipes there. So you can see a half a pint. You're talking about 1 pint is 2 cups, or what is it, 6 fluid ounces, and so on. You can see 1/8 of a cup is the same as 2 tablespoons. So again, baking or any kind of, I suppose, cooking or anything of that nature will require a good understanding of fractions. So now, equivalent fractions is the first thing that I'm going to look at. I just actually want to change my pointer here. Okay. So this is a concept, and I'm kind of pretty much now, so just 20 past. For the next, hopefully, 25 minutes or so, I'm going to look at 3 different items or ideas that you would teach when teaching fractions. The first one is the idea of equivalent fractions. The second is the addition of fractions, and the third is division of fractions. And I'm going to see how we can teach each of those topics, which are central to a good understanding of fractions, for understanding. So I really want, rather than just saying this is the rule, remember it, which happens so often, and it's where we lose so many students to mathematics. I've had this conversation numerous times this week. I've kind of been overactive nearly on Twitter with it, but there's messages out there that it's okay to not be good at mathematics, and that comes from students just seeing it as it's just a load of tricks that we have to remember. They don't see 2 things. They don't see it as a logical process, and they don't see it as a useful endeavor. And they're 2 things, and it's really, I think, this maths week that we should be trying to overcome, because maths is logical, maths is useful, but yet you turn on the TV and you'd be convinced otherwise if you were to believe what you see. There's an ad at the moment on Post that states, it opens with insurance claims or insurance details or something, or filling out insurance forms, that's what it is harder than leaving certificate mathematics. Straight away, if someone said it's harder than being able to read, no, it's not okay to say that it's difficult or that it's okay not to be able to read, but there's some acceptance out there that it's okay to be poor at maths, and that's what we need to overcome. And likewise, it was the same night I was watching Lucy Kennedy. She had Adele King, so Twink, in her house, and Adele was saying what she would have done if she didn't enter the showbiz industry, and she made some comment, and Lucy turned around and said, "Oh, what, you wanted to be a maths teacher?" And so being a maths teacher is possibly the worst profession you could enter, and it was nearly ridiculing mathematics and mathematics teaching. So I really think that in order to overcome these issues, we need to, as tutors, present mathematics in a meaningful way and show that it's not a bag of tricks, because then people will start to realize A, its importance, and B, that really logic underpins it. So again, kind of went a tiny bit off track there, but that's what the aim of this is how can we then teach these topics for understanding. So on the left hand side here, we see half an object is shaded. But is that the only way that we could shade half of this square? And again, if I was you teaching this content, or even if we were doing this workshop face to face, what I would do is I'd hand out one of these squares to everyone and ask you, okay, will you shade that half of that square a different way? And some possible suggestions that I've been given in the past when I've done this activity with whether it be tutors, adult numeracy tutors, or even my own pre-service teachers. These are some of the representations I would get back. So you can see here, that's the half that I gave them, but you could have represented 3 horizontal bars that would also represent half, or we could have represented the diagonal of a square and shaded just one side of it. But in each of these, we see that there's 36 squares, there's 36 squares in the full unit, and we see that in each of these, there's 3 by 6, so there's 18 squares represented here. We could do a similar calculation here, and again, this activity, I'm just kind of talking you through it now, but hopefully it would be a lot more interactive if we were live. But here as well, we can see we have half a square and half a square, so that's 1. We have half and half, that's 2. We have half and half, that's 3. Then along here we have 5, so that's 8. And another 4, which is 12. Another 3, which is 15. Another 2, which is 17. And there's our 18. So in each of these, 18 of the 36 squares are coloured when we wanted to shade a half. So what proportion, and again, that's going back to Adrian's definition, what proportion or fraction of the large square was shaded? So we started with 36, and we saw that when there was a half, that 18 of them were shaded. So really, what conclusions can we draw? We can conclude that a half is equals to 18 over 36. But again, drawing conclusions from just one example, doesn't work, because we could make so many conclusions. Okay, well, we add 17 to the top and we add 34 to the bottom, and then we're not, if we were to take that forward, obviously that doesn't make sense. So in order to draw conclusions from some activity like this, we need to start to see a pattern. So how do we see a pattern? Well, we consider other examples. So now what I would ask you to do is to shade a quarter, and again, I'd ask you to shade it so that one maybe is on the border and one doesn't touch the border at all. So you can see that example here. And likewise, a third. Again, I might give conditions in this case where the third has to be all connected, that every square you shade has to be connected to the other squares. Or in another example, the shaded areas are not connected. So there has to be some gap between some parts of the shading. And you might get examples like this. So again, you as the tutor can set it up in such a way that you're guaranteed to get different representations, because other students might have just shaded this line and this line, or the top and bottom line. You just don't know. I've seen students come back to me and they shade a square here, 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 just random. But what they would conclude at the end of it, what every group can conclude, is that when we're shading a quarter, there's 9 squares shaded in both examples. And I'd often get students to come up to the board and literally hang up their shadings on the board, just with magnets, and we talk through each of them then. Likewise here, we can see that there's 12 squares shaded, and the same here, we have 2 columns of 6. So now, how does that lead on from what we just did? So we saw that the same fraction or proportion can be expressed with different numerators and denominators. So what have we seen? Well, we've seen that a half is equal to 18 over 36, and we've seen that a quarter is equal to 9 over 36. So what did we do to the numerator? So again, you might have students shouting out different answers here. It might be a case, as I said, well, we added 17, it looks like. But did we do the same in both processes? Well, no, we didn't add 17 to 1 to get 9. So is there anything else that we did? So we could say we multiplied 1 by 18 and we multiplied 1 by 9. But then if that's what we do to the numerator, what must we do to the denominator? So we see here, we've multiplied the numerator by 18, but we multiplied the denominator by 18. Here we multiplied the numerator by 9, so we must multiply the denominator by 9. Now again, I'm just going to throw out a question to you for a second. Why must we perform the same operation to the top and bottom? That's the question I'd be asking students. Why is it that if we want to change, which is what it looks like at the moment, the numerator and denominator, why must we multiply the numerator and the denominator by the same number? Now, while you're considering that, so again, just if you could please just add into the chat, it would be great just to see what your insights are. In the third example, we saw that 1/3 was 12 boxes out of a total of 36. So again, does the same process hold? So if we multiply 1 by 12, we get 12, obviously. If we multiply 3 by 12, we get 36. So this process seems to be holding. Now, I'm doing a hell of a lot of talking here. That's the nature of this webinar. But of course, you'd be trying to elicit this from students. Just like I've thrown the question out to you, why must we perform the same operation to the top and bottom? But any of the questions that I have on these slides, I'd be throwing them out to students, because that's what allows them to be meaningful constructors of their own learning. So Ferguson, I might just call you in. Was there any suggestions to why we must perform the same operation to the numerator and denominator?
Yes. Adrian McGill from Dundalk, fair play, Adrian, said, so value of fraction does not change.
Excellent. That's it. We cannot, and this is where mathematics is often portrayed as that bag of tricks, where we can just multiply top and bottom by 9 and change the whole thing. That's not what we're doing. If I multiply by 9 over 9, or if it's, 18 over 18, or if it's 12 over 12, really I'm just multiplying by 1. 9 divided by 9 is 1. 18 divided by 18 is 1. 12 divided by 12 is 1. Any number divided by itself is 1. And I can multiply by 1 without ever affecting the value of the expression. Why? Because 5 multiplied by 1, 10 multiplied by 1, 18 multiplied by 1, it doesn't change the value. It's still 5, 10, 18. Again, if you want to get into more detail, it's because 1 is called the multiplication of identity, meaning it doesn't affect the number that it multiplies. But for that reason, if we do something to the numerator, we must do the same to the denominator. And that approach obviously does hold there. So again, now without ever telling students, oh, just remember what you do to the top, you do to the bottom, now we've explained it in a way that hopefully makes sense to them, and a way that draws on their knowledge of basic numbers, which is just multiplying by 1, doesn't change the value.
Niamh, can I interrupt you? There's a question here from Warren McIntyre. He said, should we look at fractions as a ratio at this stage? It would be easy to see why we have to multiply both numerator and denominator by the same number then.
Absolutely, and it all depends on your approach and what way you're sequencing your, I don't know, if it's a module or if it's a kind of a week-long program that you have. It all depends on how you sequence it. So if you're talking about ratios, so I think, so if we had, let's say, I'm trying to think of an example off the top of my head. Okay, for every 2 parts water, we had 1 part my wadi to make 1 glass of my wadi. If we wanted to make 2, we'd obviously have to double the portions of my wadi with double the portions of water, and so on. So if you were thinking of it in ratio terms, then that would be, yeah, it does make sense. And I'm hoping that might answer Warren's question. Again, Warren, if you want to add in another question, or if I didn't answer that correctly, I think I'm interpreting that right. But again, it just depends on how you sequence your teaching in terms of whether you're looking at this as a ratio or just as a fraction. But ratios and fraction are the exact same thing anyway. It's 2 objects or 2 items, for want of a better word, in proportion. So again, I might move on, but Fergus, if Warren comes back with any other question, please just interject at any time. I'm more than happy to address those questions because it makes it feel more interactive and real.
Yeah, Warren has replied, great, thanks.
Okay, perfect. And again, if anyone at any point, and I don't know if I stressed that at the start, not just to answer my questions, but if you have a question and it makes sense to ask at that point, or just you feel I'll forget it in 10 minutes time, just throw it in, and I'm happy, Fergus, for you at any stage to interject. I'll pick up my train of thought fairly easily again. So just in terms of an assessment idea for yourself. So again, this is another area with maths that, and a lot of the students or the adults that you will be teaching have probably had quite a negative experience of maths in school. We've done some work with Nala lately. It was eye-opening to see the experience that some of these students had at school, from being put down the back and just told work away yourselves, to just being given a series of problems every day to solve with no meaning or no relevance to their own lives. So one idea we came up with in the centre was fraction dominoes. And again, I can actually send the template for this on to you. I didn't send it to Fergus yet, but I happily will later on. So it's similar to a standard game of dominoes. Each player tries to match the fraction on one end with an equivalent fraction on the end of another tile that they have. Each player may only play one tile per turn, and so on. You know what dominoes is like, but fraction dominoes look something like this. So you'd be dividing these dominoes up between your students, and you could see then if this card was laid down, it would have to be maybe, let's say 9/15 was linked to 3/5, and you as a player had 3/21. Well, we can see that 1/7 is equivalent to 3/21, so we could then match that domino. And likewise, 2/4 is equivalent to 3/6, and you can just keep going. It does take a bit of planning on your part as a tutor to develop resources, but what I will say in that regard is the laminator is your best friend. Laminate these resources and you'll have them for years to come. Now, as I said, I've done a template, I've done that activity with tutors in the past, and it's gone down really well. So if you do want that template, just let me, I'll put up my email at the end, but let me know or let Fergus know, and I can happily send them on to him. If you want to put into the chat to make sure that they're sent on, that's fine too. So that's just one assessment idea. So really what I was trying to highlight there was how we just don't teach it as a rule, but instead we visualize it, we help them, or we get them to develop the rule, and we get them to be owners of their own learning. And then the third point I was trying to make was, we don't just have to send them away and say, oh, practice 20 of those questions, when they see no point in practicing just converting fractions between their equivalent form. So instead, can we come up with some novel assessment such as this that would allow them to practice the skill? That's developing their procedural knowledge, but doing so in a way that doesn't feel like it's a maths classroom, doesn't feel like they're stuck just writing out sum after sum after sum. Okay, so the addition of fractions, and I'm conscious of time here, we might only get addition of fractions done, but we'll see, we can play it by ear. So as an Aston Villa fan, it's great to finally be able to say, or to use an example. Usually we're going so badly that we can't, but this time I just said, for the addition of fractions, why not look at real life examples? So start with a real life example. And this is the problem that I have this with my own pre-service teachers when we go out viewing them on school placement. What a lot of teachers do is, and I'm not blaming these teachers, it's the way they were taught, it's been successful for them, so they go back and teach how they were taught. But what they'll end up doing is they'll teach addition, they'll teach subtraction, and it'll just be, here's how we add, let's do 20 questions. Here's how we subtract, let's do 20 questions. Here's how we multiply, let's do 20 questions. And then by the end of it, students, if they're not interested in pure mathematics, they may be turned off and say, well, there's no point in studying this. And it's at that point then that the teacher says, I'll do all the real life examples at the end. So rather than that, I try to encourage teachers, why not give them a hook at the start? Give them the real life example at the start and use that to frame your lecture, to frame your class, to frame your 40 minutes with these students. And I'm going to look now at how we could possibly do that for the addition of fractions. So we see an example. After struggling last season, Villa have got off to a great start in this year's Premier League. Many believe that this is down to the signings they have made. Two of their summer signings were Ross Barkley and Ollie Watkins. So to date, Ollie Watkins has scored 3/11 of Villa goals and Ross Barkley has scored 1/11. What fraction of Villa's goals have Ollie Watkins and Ross Barkley scored between them? So we know 3 of every 11 goals Villa have scored have been Ollie Watkins. 1 of every 11 has been Ross Barkley. So on the right, again, visualization is going to be so key. On the right, the circle represents all the goals that Aston Villa have scored. So this full circle, Aston Villa could have scored 121 goals, and this circle represents 100% of them. Now, I've divided this circle up into 11s. So you'll see there's 11 segments. And I know that Ollie Watkins has scored 3 out of the 11 segments, so 3 11ths of the full unit, and Ross Barkley has scored 1 11th. So now what I would say to students is, use this image to determine the total area of the circle that is shaded. So what proportion, again to use that word that Adrienne gave at the start, what proportion of the whole unit is shaded? So we can see there, out of the 11 segments, 4 are shaded. So what does that mean in the context of the question? Well, it means that together Ross Barkley and Ollie Watkins have scored 4 11ths of Villa's goals. And then what I would suggest doing is giving them another question, very similar to try. So another high-flying team this season are Everton. So again, you can see that thread is linking through. I kind of have a story to tell, and that story allows me to present a question to them, get an answer, and then give them a task to try. So another high-flying team this season are Everton. Calvert-Lewin has scored 6 12ths of Everton's goals, while new signing James Rodriguez has scored 3 12ths. And now I say to students, right, use any shape to represent Everton's complete number of goals, or complete kind of goals scored this season, and then shade in the proportion that Calvert-Lewin has scored and that James Rodriguez has scored. So now again, we're going from one example to a second example to see will the pattern hold. So again, you give them time obviously to do that. I'm now starting to move very quickly because I'm conscious it's 25 to. So we saw in the first example that 1 11th plus 3 11ths was 4 11ths. And 6 over 12 plus 3 over 12 is 9 over 12. So that's what we've seen. So are we starting to see a pattern emerge? So can you see any patterns between the fractions we are adding and the solution? And again, any of these questions is what I'd be thrown open to the floor and really trying to elicit the information from the students. What do you notice about the denominators in each of these cases? Again, you're hoping for suggestions like, well, the denominator is the same in both of the terms on the left-hand side, and it actually is the same in the answer. And what do we notice about the numerators could be another question. And this is what I was talking about, this consolidation. So you see this title here is Drawing Conclusions. This consolidation of learning is really important because you can see as many patterns as you want, but until you draw a conclusion from those patterns, the students aren't going to get much from it. So in their own words, and this is where students are constructing their own learning. When adding fractions with the same denominator, we must. And you ask the student, you finish that sentence and you write it in your copybook or whatever it is you're working on, and that's how you remember how to add fractions with the same denominator. Now most will say you add the numerators, others might come up with something slightly different, but it's their way of, or it's their vision of what's happening. Now you have to obviously as their tutor make sure it's mathematically sound, but once it's mathematically sound, it's fine, they can write it. It's not that we have to have this definition of how we add fractions. Students can come up with their own based on this pattern. So what could we then do? Oh, sorry, if we had a very strong group, and again, this might just be for a student. I often find even in my own teaching that you'll have one student just going, well, why does that actually work? Like, what is the real logic or the real mathematical meaning behind it? Not every student will care about that. Some students, if they just figure it out for themselves, they're happy enough to go away and take it. Look, I've spotted the pattern. I've managed to figure out what we have to do. That's enough for me. But what I have included here, and again, it's just for your own perusal, is how we could explain this algebraically. And again, it might be an idea for when you do move on to algebraic expressions, because again, that's forming the link. So again, you might be doing level 4, algebra level 4, whatever it is, but this could be a nice example of factorization and forming that link back to fractions. So do both expressions have a common factor? What is it? So we can see here that 1 over b is common here and 1 over b is common here. So we can take out our common factor, just like we would when factorizing expressions. So we take out 1 over b, we're left with a plus c. Now, if we add 2 integers, we're going to get an integer. That's like if you think of a number line, if we're just adding an integer, a whole number to another whole number, we're guaranteed to get a whole number. No questions asked. We're never going to fall into the middle of a number line. So a plus c is just going to be some integer t. So we could replace a plus c with some integer t, meaning that my answer is t over b, which is just a plus c over b. Now, I am not saying that this should be done with every student at every level, but it's just for you to have, as a tutor, that you're equipped with that understanding. And you can share it if the need arises, or you can just park it and say, at least I know it's there. So just an idea for you. Again, I just said I'd include it in the slides. Okay, now we're going back to the football. And again, I'm still focused on addition. I'm actually probably not going to get onto division, and Fergus, we might have a chat about that later on if I could do a screencast or something if you want for the division, but I think it's better just to look now and finish off addition. So we look here at, in Liverpool's title winning season, Van Dijk and Firmino scored 3/15 of their goals, while Salah and Henderson combined to score 6/20. Now, what proportion of Liverpool's goals did these four players score between them? So we just think, and our students are just thinking, bingo, I've got my head around addition of fractions. Never understood it before, I'm getting to it now. And then we throw this at them. So we start with the same approach. In what way does this recent question differ from the last one? So again, you'd be asking, do you notice anything different? You'd be hoping for them to recognize, well, the denominators aren't the same this time. So we'll try the same approach. We'll try to visualize it first of all. And we see here this graph, 3/15 of the object is shaded red, so that was Van Dijk and Firmino's contribution, and we see 6/20 of the object is shaded blue, so that was Henderson and Salah's contribution. And we ask the same question, what fraction of the shape is included? So we see that there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So the shape is divided into 10 parts. We definitely have 5/10 shaded. We can see a full 5/10. But how are we going to work this? How are we going to figure out what proportion of 1/10, say, is shaded red here and what proportion is shaded blue? We've come across in a sticky situation. We can't actually say what fraction of the shape is shaded in total. And why is it that we can't use the same approach? Why is it that we can't just say, well, there's 4/11ths or 9/12ths? The reason is because they're not all in the same unit. The last time they were all 11ths or they were all 12ths, but now we have 15ths and we have 20ths. That's the issue. So how do we overcome this? So since we're not dealing with fractions with the same denominator, we have to come up with a new approach. Not a brand new approach, just a slightly different approach. And a nice way that you could introduce how or what this approach will entail is to give them this story. So you've decided to travel from Limerick to the Giant's Causeway in Northern Ireland. The route you opt for is to travel on the M7 to Dublin, merge onto the M50, and in turn onto the M1. Continue on the M1 in the direction until you merge onto the N1 when you enter Northern Ireland, and continue on the N1 or A1. So the AA have outlined that when travelling in the Republic of Ireland, you will cover a distance of 286.8 kilometres, while when travelling through Northern Ireland, where distance is measured in miles, the distance covered was 285 miles. What was the total distance travelled? Why is this question difficult to answer, and how could we address this issue? Again, even if just one person wants to jot down a couple of answers to those questions, and we'll have a look at it from there then. So just see what you come up with, what suggestions you have, just for 30 seconds even. Fergus, if there's one response, then you can just shout it out and we'll just move on from there. I am conscious of time, so whenever there is a response, we might take it and run with that.
Okay, yeah, nothing so far.
Yeah, no, I know it'll take time even to type it up, but before I move on to the next slide, and this, I'll just go through one or two more slides then before opening it up to the floor.
Okay, Niamh, we've got an answer from Enda. Thanks, Enda.
Thank you.
Different units make it difficult. Convert one of the distances to the other unit, e.g. kilometers to miles. Similar answers coming in, and Sarsfield saying conversion factor. And Adrienne is saying one is represented by miles and the other by kilometers.
Excellent. That's it. You've all hit the nail on the head. The issue is with the units. We have two different units, kilometers and miles. And again, students that you're teaching will recognize that straight away, because again, that's a problem that they may encounter. That's something that makes sense to them. So it's difficult to answer because we have different units. How could we address it? Two people, I think, said, why not convert one to the other? That's how we solve real world problems, when we have two different units. So how then is that related to our fraction problem? Well, we have two different units, so can we convert them to the same unit? So we need to find a common multiple for both of our denominators. So we need the same denominator, because we know how to add fractions when we have the same denominator. And now we're back to this idea of equivalent fractions. So what strategy could we use? So remember, we have 15ths and 20ths. We need to find a number that both 15 and 20 divide into. And again, I would leave that up to your students. Some of them might just multiply 15 by 20 and get 300, and that's fine. That works as a common denominator. It's not the lowest common denominator, but it is a common denominator. Others might see, as I've suggested here, that 60 is the lowest common denominator. So 60 is divisible by 20 and 15. So then, in order to get 15, to convert 15 to 60ths, we'd have to multiply the denominator by 4. But if we multiply the denominator by 4, we must multiply the numerator. Again, you see my note there, we're still only multiplying by 1. And likewise, in order to convert 20 to 60ths, we multiply 20ths by 3. But if we multiply the denominator by 3, we must multiply the numerator by 3. So we get 18 over 60. Now we're back to the problem we had with Aston Villa and Everton. Now we have the same denominator. So now we see that 3 15ths plus 6 20ths is actually equals to 12 over 60 plus 18 over 60, which is 40 over 60, which is 2/3. So now we can conclude that in fact 2/3 of this entire shape was shaded. And again, I just give another example there. I know my examples were very sport orientated for the addition of fractions, but you can see two different recipes there. And again, I just talk about the subtraction of fractions. So again, it's the inverse of addition, and so we use a similar approach. So I'd be getting students to elicit the approach that we use. And finally then, for some consolidation activities, so that is activities like the dominoes, event that we had. There's some games there, some activities, some downloadable worksheets that might help you to create an innovative activity. And another example that again has worked well is bingo. So each person receives a bingo card, and on this there are a series of fractions. A series of questions will be posed, and if the answer is on your card, mark it off. The first person to complete 2 lines on their card will be deemed the winner. Now again, I have created these bingo cards for previous workshops, so if anyone wants the template, I'm more than happy to send it on. That can be the most time-consuming part for tutors. But then what you can do with that kind of activity is give them, remember we said it's important to understand procedures as well as application. So give them procedural questions where they have to add 2 fractions without any context. And then we can include 1 or 2 real-world problems. So you can see an example there. Now I've actually run 5 minutes over with still about 15 slides left to do. I'm going to stop there. Again, I know we've only touched on 2 topics in fractions, but I will be more than happy to do a recording, so do a kind of screencast and make a video available on basically how I would have spoken or talked through the fractions. Again, I can talk to Fergus about that, and if he wanted or if he feels it might be of benefit to people, I'm more than happy to do that. So what I would like is, sorry, Fergus, do you want to jump in?
What about maybe giving another 10 minutes and going through them, or would you rather stop and take some questions?
I suppose I can throw it out to them or to the tutors if you want. If you want to say continue or questions, if you just type continue or questions in, I'll go with whatever you want. That's, I think, at least then it would be meeting their needs.
Good point. Okay, Adrienne said continue. Everyone's saying continue, continue, continue. Catherine.
Okay.
Catherine's.
Okay, if anyone needs to leave at any point and has a question, you can pop it into the chat, and I could even email you an answer if you do need to leave. So I'll continue, so Fergus, and you just cut me off whenever. I'll go through this fairly quickly, just to give some more ideas.
Thanks a million.
Okay, so the next thing I wanted to look at was the idea of division. And as I said to you previously, a lot of times students really, and I see this with first year students coming in, they really struggle with division. They've got so dependent on the calculator that when they try to do algebraic division, it's a nightmare. But the reason being, they struggle to understand what we actually mean by division. So what do we mean when we divide 8 by 2? What does that mean? Again, I would throw that open to you, but we're going to try and keep going. What are we finding out when we divide 8 by 2? Everybody that you meet could probably tell you 8 divided by 2 is 4. Grant, no problem. But what is it we're doing? We're trying to see how many groups or lots of 2 are in 8. So again, we just look, if we had €8, how many lots of 2 are in it? There's 1, 2, 3, 4. So how many groups of 2 or lots of 2? How many 2s, or how many times do 2 units appear within 8 units? That might be the best way to describe it. So how then does that fit in with fraction division? So let's say, again, just looking at a real life example to kind of start us off, the Finn family are tiling the floor of a new shower. The area of the floor is 1 square metre. You can imagine a shower, 1 square metre, and the area of each strip of tile is 2,500 centimetres squared, or a quarter of a square metre. So how many tiles should the Finn family order? So there's our tile. So each of these is a square metre. Each of these is a quarter of a square metre. So how many do you think they should order? Again, would love to be in front of you just to see your kind of answers. But really there, if we were to fit them in, and you can give students these physical, like you could cut out tiles and the obviously a scale version of a 1 metre squared shower floor, and you can get them to fit them in. So we see that we needed 4 of these tiles to fill the metre squared area. So what can we conclude? What mathematical operation did we just perform? It was division, because we were seeing how many quarters fit into 2. So, sorry, fit into 1, apologies. So 1 divided by a quarter is 4. That's our very definition of division. How many quarters fit into 1, just like it was how many 2s fit into 8. So how then can we go on with that? So what does 2 divided by a half mean? Again, it's the language that you're constantly reiterating. What does it mean? It means how many half units are in 2 units. So there's our 2 units, and we have 4 half units. So we see that 2 divided by a half is 4. Now we haven't gone beyond basic division here, okay, and visualization, which is obviously key. Now we're going to say 2 divided by a quarter. But what does that mean? Well, I have my 2 units. Now I want to see how many quarters fit into them 2 units. So sorry, I just did 2 new units, and this time I divide them into quarters, and I see that there's 8 in total. So that means that 2 divided by a quarter is 8. What does 3 divided by a quarter mean? Same thing. How many quarters are in 3? And again, I'd spend a lot more time on this, but I'm just giving you ideas for now, and hopefully that's okay. Again, if there's anything else I can do to kind of supplement, let me know. And then 3 divided by an 8. So we're cranking up the complexity a bit. We can see 3 divided by 8. So we have 8 here, we have 8 here, and we have 8 here. So in essence, we have 24. And again, now we've started to try and establish a pattern. But we need some consolidation. So we see 2 divided by a half is equal to 4. 2 divided by a quarter is 8. 3 divided by a quarter is 12. And 3 divided by an 8 is 24. Can you identify a pattern? And again, this doesn't need to be 100% mathematically accurate when the students are first giving it. What some of them might say is, well, it seems to be, initially they might say 2 plus 2 is 4, but then, well, that doesn't hold here, so we're going to have to go back. How else do we get an answer of 4? And some might say, well, you multiply the denominator by the whole number. And now, that's not entirely accurate because it won't hold going forward, but for now, it would work. We multiply the denominator by 4, and in this case, we multiply the denominator by 3. So let them come up with their own, definition of what they think they're doing. And then you as a teacher are going to help them to refine that definition based on more work that they do going forward.
Niamh, I've got another question from Warren McIntyre. He's saying, how do you view the approach of 8 sweets divided by 2 people, rather than how many times does 2 go into 8? Can we marry these approaches?
Okay, sorry, I'm just going to jot that down just so I can even visualize it. So 8 people divided.
8 suites divided by 2 people, rather than how many times does 2 go into 8?
Yeah. So you're saying, so that the question then really that you'd be posing, 8 suites would be 4 suites per person. So 8 divided by 2 would give you 2 groups of 4. So how then, just to, again, I'm thinking out loud here, 2 divided by a half would mean that, yeah, you can marry them approaches. The only thing, when you use examples like people, and then if you're using that to try to move on to fractions, the issue becomes what happens when you have half a person, if that makes sense. So that is why a lot of the time we just look at the idea of units and seeing how many objects fit in a unit. It's probably not a great answer to the question. I'm just.
Well, Warren says makes sense. Thanks.
Okay.
So
yeah, Warren, again, I might even just take that question away and just see, is there any way that, because I do like the idea of starting with, again, that's something that they've done before, just like the miles and kilometers example. So I do like the idea, but I just know that issue of having half a person is where we can run into difficulty. But if I can see a way of manipulating it, I'll get back to you on that definitely, because that is a really good analogy and a good question to see, can we link the two?
And we've about 2 or 3 minutes left, so maybe if you finish up, and we won't take any more questions, I'd suggest, because they seem keen for you to continue.
Okay, yeah, and again, I'll put my email, I'll shout out my email at the end if anyone wants to follow up with anything. So what I was going to do then, how I would suggest you move on, would be to link what we did on the previous slide, so just dividing whole numbers by fractions, and then moving on to try to divide fractions, a proper fraction by another proper fraction. And there's numerous ways to do this. Again, if I was with you face to face, I'd show you manipulative such as cards and elastic bands, but another way is a fraction wall. So I'm just going to show you 1 or 2. I was going to show you how to create fraction walls, but we just don't have time for that. So a half divided by a quarter. So we see here, actually, just let me change my pointer. So here we have a half, and here we have a quarter. So what we do with it, and this can take a bit of time to get used to, but if you can get your head around it as a tutor, it can be really, really good learning experience for students when they get their head around it, and start with basic examples. So a half divided by a quarter. So we see the line where the half is, and we see the line where the quarter is, and they're actually aligned. That won't always be the case. So this here is a half. Now what we're looking for is to see how many quarters are in a half. So this here up to this point here marks a half, because the lines are aligned, and we can see that there's 2 quarters in a half. So that means we can conclude that a half divided by a quarter is equals to 2. Now that's the most basic example. So now let's see a quarter divided by a half. So we want to see how many halves fit into a quarter. So we can obviously see, if we're to do a dotted line, okay, so that's a quarter. So we want to see if any other line, okay, so we can see there now everywhere where the quarters and the half align. So again, because these line up perfectly here, this is a half, and we want to see how many halves are in a quarter. So really, a half is made up of 2 parts here, and one of those parts fits in a quarter. So a half of a half is in a quarter. So this is a half of this full half here, because that half is divided into 2 parts. So a quarter divided by a half is a half. Now I was going to go on to some more examples, but it is just 12 o'clock. But you can use that same approach for each of these. And you see I've kind of altered the fraction walls. I changed the last line from 8 to 12 because the numbers changed up here. Now again, that might be a bit rushed. If you want any clarification on that, I'm more than happy to take questions or to answer. My email address is Niamh, Niamh.O'Meara, Omeara, @ul.ie. If you look up my name on the UL website, it'll pop up anyway. So I'm more than happy to answer any questions that you have on that. So what I'm just going to do now is I'm going to stop sharing my screen, and I will be back to you. So, okay.
Niamh, thanks very much. That was fantastic. I can see by the comments and by everyone staying with it till the end that they really got a lot from that and enjoyed it. Lots of positive comments coming in. I'm sorry that we hadn't time for more questions, but because you built questions into the main presentation, we had plenty of input from the attendees. So it just leaves me to say thanks very much, Niamh, for a wonderful presentation full of really practical and great examples that you can use in the classroom. Hopefully everyone's got a few ideas, a few things they can try. And thanks everyone for tuning in. We've got webinars again on Thursday and on Friday. So thanks everyone, thanks Niamh, and
Thanks to all.
okay, bye bye everyone. I'm going to end for all now.